Hello, my name is Josh Yazman. I'm here to present the results of my midterm for Predict 454 in Northwestern's Masters in Predictive Analytics program. The project that I took on was to predict both point spreads and win probabilities in college basketball. And I picked this project for a number of reasons. Including personal interest in college basketball on my part, and also the timing of this project is sort of ripe for coming up with some really good predicted win probabilities before March Madness. This video will go over sort of some of the data cleaning and infrastructure steps that I had to take to format the data appropriately. And then I'm going to briefly touch on the various point spread regression techniques that I've applied to this problem. And then the real meat of the problem is classification. So I want to apply this to college basketball brackets for the NCAA tournament. And so classification is slightly more important in that context than point spreads. So without further ado, okay, so I will also be posting a write-up of this project on Medium if anyone wants to take a look at that. But essentially, I started out with this premise that the best way to predict who is going to win a college basketball game is to actually try and predict who is going to score the most points. That seems intuitive, but it's also a strategic choice that I made in terms of sort of lining up the types of models that I built first. I first attempted to predict the relative number of points each team would score, and then use that in a set of classification models. It turned out to actually be a little easier to go the other way around. So it was slightly easier to predict win probabilities and then apply those probabilities to point spreads. But we'll get to that towards the end. So talking about the data involved in this project was all downloaded from sportsreference.com. Sportsreference.com has these awesome game logs for each team for each season. They show one row of data per game, including the opponent, how many shots your team took versus the other team, how many points your team scored versus the other team, over across it. I think I want to say about 30 different statistics. So I downloaded those game logs for 2014 through 2018 up until mid-January when I actually downloaded the data. And I consolidated all of that data to spreads. So instead of having points for and points against, I consolidated those fields to point spread. So if you score more points than the other team, that number would be positive. Otherwise, it would be negative. I also made a conscious choice to do a couple of things. So for one thing, I wanted to make sure that the data that I was using to make my predictions is as close to relevant to a real world bracket predicting situation as possible. So instead of using actual outcomes for prediction, I only use the data that we would know prior to the game. So the example I give in the Medium post is, instead of, if I wanted to predict Villanova's 12th game, I would keep their real point spread as a sort of validation tool. But as an input to that model, I would only use the average point spread from the 11 games prior in that season. So that was suggested by a couple of different papers that have demonstrated success in classification modeling, and so I adopted that practice myself. Another data cleaning step I took specifically to address some concerns that I had heard from outside experts was that I used the 2014 to 2017 data as a training set, and I used this year's data as the test set. And the reason for that is there's a school of thought that college basketball teams change too rapidly to accurately predict their performance. I actually have a pet theory that the composition of teams doesn't change that much. It's just the characters, the names of people on the court. But I haven't proven that empirically yet. So as a way of, again, sort of quelling some of these concerns, I wanted to use the last 3 years worth of data to predict this year, as opposed to keeping everything in the season. That also allows me to get a little bigger of a sample size. And then the last thing on here, I had done some previous analysis to see when the average level of each statistic in college basketball sort of levels out. So team performance is highly variable at the beginning of the year and sort of levels out towards the middle of the year. There's a lot of reasons for that. Coaches experiment with different playing strategies. Duke is going to play, Our Lady of Mercy, towards the beginning of the season, towards the middle of the season, Duke is going to play Virginia Tech and UVA and good teams. So I made a conscious decision based on that analysis to only look at games that came after the 11th game of each team's season. So the first 11 games of every team's season is used to calculate the average of each stat, but beyond that, it's not used as training data. So again, just to briefly touch on the regression methods that I use, point spread prediction is a little bit more lucrative in terms of betting markets as opposed to classification modeling. But I also found that it was a little more difficult. So I think the main takeaway from this project is some good classification modeling. But to touch on some of the regression attempts that I made, the first is a heuristic variable selection. It's just multiple linear regression with variables selected through my own domain expertise as well as some exploratory analysis. I've used So I used the 4 variables here, the 4 predictors that show more than a 0.1 R squared, correlation with actual observed point spread. And those were average point spread prior to the game, average field goal percentage spread prior to the game, average assist spread prior to the game, and average defensive rebound spread prior to the game. And that model turned out to be pretty bad. The correlation coefficient on it was in the 20s, and as you can see from this, this is a GG pairs plot from the G-Galley R package, and essentially what it does is it shows the pairwise distribution of all variables included in the model, as well as the observed point spread and the error. So we can see on this bottom row here, this is error on the y-axis and the various predictor variables on the x-axis, and error rates are highly correlated with the observed point spread. So that's bad. That violates one of the that violates one of the core assumptions of linear regression. So that model is almost definitely not going to be good. Lasso regression it involves sort of starting with all of our predictors and using a constraint to shrink those predictors down towards 0, or actually shrinking them to 0 if that's appropriate. So the optimal constraint value, which I found through cross-validation and trial and error, was 0.0103, and then applying that constraint, we got a whole host of lasso coefficients. We got some that were shrunk to 0, including I think 1 or 2 that I actually used in my heuristic model. So egg on my face for that. The next model that I attempted was least angle regression. So least angle regression, if we recall from ESLR, starts with the variable that has the highest degree of correlation with the target variable with point spread, and then adjusts the coefficient for that predictor until another variable has a higher correlation, and then it goes through that process until every variable has had a chance to be included to some degree. The output of that, the coefficients that were included in that model were somewhat similar to my heuristic model, a little bit different and better. And then the last two here that really increased the performance of my regression model to the extent that it was possible are boosted regression trees and random forest. So these are sort of similar in the way they're structured. Boosted regression trees sort of start with they start by dividing the data on the variable and division point that most reduces, that minimizes residual square or residual sum of squares, and then iteratively does that as many times as you let it. So again, through cross-validated trial and error, I found that the optimal sort of depth or the optimal number of times that the boosted regression tree should split my data was 6. And then I trained a model with 10,000 trees at that depth of 6 layers. And then the last thing I did here was random forest. Random forest, again, works similarly to boosted regression trees, except instead of cutting off a node depth, random forest just builds the entire tree as far as it wants to go. So evaluating those models, let's see if I can zoom in here. So they all generally have a positive relationship with observed point spread. That's what we're seeing in figure 6 here. But if you look at the individual distributions, all of these predictions have 2 problems. One, they're much more conservative than the actual observed point spread, and 2, they center around 0, and there are no ties in basketball. So this isn't like soccer or hockey. All outcomes have to evaluate to one team scoring more points than the other, which is why if you look at the distribution of point spread, there's a dip at 0, and then it sort of goes back up and out. None of the regression models sort of shared that characteristic, which is a little concerning about their accuracy. The one saving grace here is if looking at figure 8 here. This is a box plot distribution of the predictions from each model based on whether the game turned out to be a loss or a win. And while there's not like a huge, the observed point spread, obviously since one team has to score more points than the other to win, the observed point spread has a clear delineation here where, after a certain, once your point spread gets down to 0, you lose the game. These predictions all have sort of predicted point spread values that straddle 0. Either for wins or losses, which isn't great, but the lasso, the random forest, and really all of these regression models do separate out a little bit from point spread. And then the last sort of evaluation step I took for my regression models was to say, if the point spread, if the predicted point spread is exactly what we say it is, and that team wins, the other team loses, what's the classification accuracy? So how many just based on that output alone, how many games should we expect to predict accurately? The accuracy isn't terribly great, but it's slightly better for random forest than the others. So I'm going to use random forest as an input into the rest of my classification models and move on to that. So for classification, I use some of the same exact models as the regression context, except altered for the Bernoulli distribution and the binary family of variables, as opposed to the Gaussian distribution for continuous variables. So in this case, random forests and boosted trees performed almost identically. The lasso regression model is sort of middling here. You can see some separation, but ideally you would want a blue lump all the way over here with no green nearby, and a green lump all the way over here with no blue nearby, because green stands for loss and blue stands for win. So we want our winning outcomes to center around 1 and our losing outcomes to center around 0. That mostly happens with the two tree-based methods, but that doesn't happen at all with lasso regression. So setting a cutoff of 50%, which means we say, everything to the right of 50% we're going to count as a win. We're going to predict as a win, and everything to the left we're going to predict as a loss. So using that constraint, or using that sort of cut point, there are some slight differences in the performance of these models. Not as much as I would have expected, but there are slight differences. So lasso the lasso model tends to sort of err on the side of a type 1 error, where we are passing up a true positive. So the prediction is negative, and the outcome is actually positive. Random forests and boosted trees sort of do the opposite. So in the sense of sort of giving us a false sense of confidence in our team's winning, boosted trees and random forests might be bad for that. But boosted trees and random forests also just generally give more extreme predictions. So some more research is going to be necessary to figure out which of those is best in a gambling context or a prediction context in terms of brackets. Okay, so my conclusion is that the classification trees worked better in both the tree-based methods worked better in both the regression context and the classification context. One thing that I would like to try in the future, because betting against the money line or betting against the point spread is more lucrative than betting against the money line. So getting the regression problem right is more important than getting the classification problem right in terms of betting on individual games. I would like to actually go back and apply the predictions from my classification model back to the prediction model, and I have a theory that I want to test that doing that sort of iteratively. So using the classification output that is decent to model point spread better, and then use a better point spread projection to model classification better, and then vice versa, back and forth until I have a theory that if you do that enough times, we'll get to a point where the classification error rate drops, to some degree, maybe moves towards 0, and the mean squared error of the point spread regression also moves towards 0. But that'll have to be for another day. So thank you for listening to this. I hope you enjoyed, and keep a lookout for some more college basketball prediction work from me.